So last day we did an introduction to functional programming. We looked at what it is and where it actually came from. And we also did a bit of a taste of Haskell. I showed you the quicksort algorithm, which we're going to come back to later on. So what we're going to do today is we're going to introduce the Haskell system that we're going to be using in the course. So the system we're going to be using is called the Glasgow Haskell compiler, or GHC for short, and it's the leading implementation of the Haskell language. There are other systems available for Haskell, but GHC is by far the most developed one. It's been developed intensively over many decades. The system comprises two parts. There's a compiler and an interpreter. And I'll just refresh your memory about what these words mean. So both a compiler and an interpreter run your code, but they do it in slightly different ways. So a compiler translates your code down to a lower level language, which your machine can then execute directly, whereas an interpreter just runs your program directly. So they're kind of two different sides of how you run programs. So we're going to be primarily using the Haskell interpreter in this course because the interactive nature of the interpreter makes it very well suited for teaching in this course and for prototyping, which is the kind of thing you're going to be doing. You're going to be writing kind of in the end of this course about one page of Haskell. But as we'll see, you can do a lot in one page. So the GHC system is completely freely available. If you go to this web address here, haskell.org/platform, you can download it for yourself for any system which you have. It's completely freely available and it works on any system. However, if you don't want to install it yourself, which I suggest that you do, or you have problems with installation, it's already on all of the lab machines in the computer science department and all of the servers as well. So you can always access it like that if you prefer. So in order to start GHCI, the interpreted version of the compiler, what we're going to do is start up a terminal command prompt. So for me on my Mac, a terminal command prompt is $. So I open a terminal window and I simply type GHCI, and that will start the system up. So if you've installed it correctly, then you'll get a little welcome message and it will tell you the version number which you're using. And then it's sitting there waiting for you to ask it to do something. So it's an interactive dialogue that you have with the GHCI system. So the greater than sign is the prompt, and it means that the interpreter is now ready to evaluate an expression. So this kind of dialogue that you're going to have with the system, if you've used a language like Python, this is something you're probably already familiar with. So the simplest thing you can do with the GHCI system is just use it as a simple desktop calculator. So you could ask it to evaluate some simple numeric expressions. So we could say 2 plus 3 times 4, and it knows that multiplication has higher precedence than addition, so it does the multiplication first. 3 times 4 gives you 12, then you add on the 2 and you get 14. Of course, in the second example, if you want to override default precedences, you just use brackets for that. So you can do 2 plus 3 in brackets times 4 and you get 20. And if you wanted to do something a bit more complicated, here I'm just taking the square root of 3 squared plus 4 squared. So these examples also show you that as with other programming languages, Haskell has more than one kind of numeric type. We see integers in the first two examples above, and then we see we're using floating point numbers down the bottom with the square root example because 5.0 is a floating point number. Haskell has many different numeric types, and we'll see some of these next time around when we start to look at types in more detail. So what I want to do for the next few slides now is introduce you to what's called the Haskell standard prelude, or the standard library. And the idea here is that Haskell comes with a large number of standard library functions, and of course you have all the familiar numeric things like plus and times that we've just been looking at, but many of the library functions which are provided as standard actually operate on lists. So a list is just a sequence of values of the same type enclosed in square brackets, as we saw last time around. So what I'm going to show you is about 10 of the most commonly used library functions on lists. And something I've done for you is if you look on the web page for the module, which is freely available to everyone, not just students studying in Nottingham, you'll find I've put an abridged version of the standard prelude, and that's about 10 pages, and it's most of the standard library functions which are commonly used. And I put a little description in there of what these all do as well. So this is a really useful kind of cheat sheet for you. When you're learning Haskell, it takes a bit of time to get used to the new syntax and to think about what kind of library functions you have. So if you ever get stuck, just have a look at the standard library on the web page and you'll probably find something which helps you in there. So what we're going to do then is we're going to look at about 10 standard library functions. So the first one of these is head. So you can see here the little GHCI prompt, the greater than sign, and we're simply applying the head function to the list 1, 2, 3, 4, 5. And it simply gives you back the first element of a list. Very simple. The dual of the head function is called tail. So tail takes a list and it removes the first element from the list. So in the case here, it removes the 1 and then we get the 2, 3, 4, 5 back. So remember in Haskell, if you want the first thing in the list, you take the head. If you want to remove the first thing and get everything else, that's called taking the tail of the list. So the second example here is indexing into a list or selecting the nth element. So the syntax for this is an infix operator, double bang or double exclamation mark. So you write a list like 1, 2, 3, 4, 5, you write double bang, and then you write an index, and that will give you back the element at that index. And you can see from the example here that as in most programming languages, and actually in computer science in general, we start counting from 0. So 0 is the first index. So the number 1 in the list is at position 0, the number 2 is at position 1, and the number 3 is at position 2. So when we index in at position 2, we get the number 3 here. So as usual, remember, indexing starts from 0. So the last example here illustrates that functions in the library may have more than one parameter, and you don't need any space, you don't need any brackets around these, as we're going to talk about in a bit. So what take does is you give it an integer, like 3, and you give it a list of things, and it just removes or gives you back that many elements from the start of the list. So if you want the first 3 elements of a list, you say take 3, and it will give you the first 3 things of the list. Very useful function. The dual of take is called drop, and drop does exactly what you'd expect. It just removes the first n elements from a list. So if you drop 3, you just remove the 1, 2, 3 in this case, and you'll get back the 4 and the 5. Then you can also calculate the length of a list. That one's self-explanatory. And the last one here is an interesting point to make. So summation is obvious. You just sum up numbers in a list. If you sum 1, 2, 3, 4, 5, you get 15. But you can think, well, what happens in the trivial case? What happens if you applied the summation function to a list with nothing in it? So the empty list. So that's just sum, open square brackets, close square brackets with nothing inside the brackets. Well, the Haskell designers could have just decided that that's an error and made the system crash, but they didn't. They decided that the sum of the empty list is 0. And that's an appropriate value because 0 is the so-called identity or unit for addition. And that simply means if you add 0 onto anything, it doesn't change it. So 0 plus 3 is the same as 3, and 3 plus 0 is the same as 3 as well. So 0 is the identity for addition. So Haskell's very careful about these kind of base cases, and it tries not to crash. It tries to give you a reasonable result. And in this case, the reasonable and appropriate result is summing an empty list is 0. Then we have product, does exactly what you'd expect, but this one's got a different base case or empty list case to summation. If you take the product of a list with nothing in it, so the product of the empty list, you get back 1. And the reason is that 1 is the unit or identity for multiplication. If you multiply any number by 1, it doesn't change the number. Okay, so again, in Haskell, we think very carefully about these edge cases, or as we'll see when we come to thinking about recursion, these are base cases for recursive definitions. Then we see 2 functions we've already seen last time around. Here's the append function for lists. It just joins 2 lists together. It's an infix operator as well, as we saw last day. And we can also reverse a list that does exactly what you'd expect. If you reverse 1, 2, 3, 4, 5, you get 5, 4, 3, 2, 1. Very, very straightforward. So what I want to do now is think for a while about function application, because Haskell is a functional language, so function application is the basic computation mechanism. We just apply mathematical functions to arguments and we get results. So let's look a bit about the notation which is used for function application. So first of all, in mathematics, you'll remember from your school time, function application is denoted using round brackets or parentheses if you want to be fancy. And multiplication is denoted using juxtaposition, and that's just a fancy word for writing things right next to each other, or you might write things with a space between them. So function application in maths is written using round brackets. So the example I've given you here in the little blue box is we're applying a function f to two arguments, a and b. So I put the arguments in round brackets separated by a comma, and then that will give me a result. And then I'm adding that result onto the product of c and d. So I just write c and d right next to each other. I've put a space between them here, but in maths books, often they would just write c and d jammed right up together. So in mathematics, function application is denoted using round brackets, and you comma separate the arguments. In Haskell, function application is the most important thing that we do. It's the fundamental computation mechanism, so we give it a very lightweight syntax. And in fact, function application in Haskell is just denoted using spacing. So if you have a function and you have arguments, you write the name of the function and then you just space out the arguments. You don't need any brackets typically, and you don't need any commas either. So because now spacing is used for function application, we need a special symbol for multiplication, so we just use the normal multiplication symbol, star. So if I was to write what I had on the previous slide, which is here, f brackets a comma b plus c times d, if I was to write that in Haskell syntax, this is what I write. I just write f, a, b, and I just space the arguments out. I don't need any brackets, I don't need any commas this time, but I then do need to put an explicit multiplication symbol in. And you can see already, I mentioned in the first lecture, Haskell tries to be very concise in terms of its syntax, and you can see already there's fewer symbols here than there were here. So the basic message is function application is the most important thing, so we give it a very lightweight syntax. You just separate the arguments by spaces. There's only one other thing that you really need to know about function application, and that's that it's assumed to have the highest priority of all. So when you learn about arithmetic at school, you learn that multiplication has higher priority than addition. So you do multiplications first, and then you do additions. It's the same kind of idea here. Function application has higher priority than any other operator in the language. So it's a simple rule that you need to remember. So when I write down something like we have in the blue box here we have fa plus b. There's really two operators there. There's the function application, which is sitting after the f, there's a space, and then there's the plus operator. So you could interpret this in two ways, as you see in the little speech box here. Either you could do f of a first, in brackets, and then add b, or you could do the a plus b first, in brackets, and then apply f to the result. And these would give you two potentially quite different results. And the one that Haskell will give you is the first one here. So if you write fa plus b with no brackets at all, the way that the system will interpret that is it will do the function application first. So it will apply f to a, that will give you a result, and then you add the result of that on to b. So it takes a little bit of time to get used to this idea of function application. So what I've given you is a little cheat sheet here. So if you get stuck, you might want to have a look back at this from time to time. So what we have on the left-hand side is we have the kind of thing which you would write in mathematics when you're applying functions in various different ways. And then on the right-hand side is the equivalent thing that you would write when you're doing Haskell. So let's look at a few of these. So the first one is just applying in mathematics f to x. And in maths you write f brackets x. Okay? In Haskell you don't put the brackets in, so you just write f space x. Nice and simple. The second one is also nice and simple. In mathematics, if f was a function of two parameters, you would write f brackets x comma y, close brackets. In Haskell, you don't need the brackets, so you just write f x, y with spaces in between them. Nice and easy. The third one makes an interesting point. So f brackets g brackets x on the left-hand side. What is this doing? So what we're doing is we're taking an input x, applying a function g to it, that will give us a result, and then we're applying the function f to that result. So we're kind of cascading or composing two functions together. And this is the same on the right-hand side when we do this in Haskell, except we need fewer brackets. all we do is we put the brackets around g of x, which forces the application of g to happen. So g will be applied to x, we'll get a result, and then f will be applied to that result. And note that we do actually need brackets around the g of x in the third example, in the Haskell case. If we just wrote f space g space x, that would be valid Haskell code, but it's not what we intend here. What that would mean is f was taking two parameters. The first one was called g, so that's a function, and the second one was called x. And that's not what we intend here. We want to cascade the two functions together. We want to apply g to an input called x, get a result, and then apply f to that. So sometimes you do need brackets, like we see here. And I'll leave you to look at the last two examples for yourself, but the takeaway message is, look at the mathematics column, riddled with brackets. Look at the Haskell column, there's only 4 brackets here. So things become a lot more lightweight in terms of the syntax. But again, if you get confused about the function application notation, what we find is that once you've been writing Haskell for a few weeks, it becomes very natural and you won't need to think about this anymore. But if you need it, have a look back at this little cheat sheet. So what we're going to do now is think about how you actually write Haskell programs in practice. And you do these in what's called Haskell scripts. So as well as functions defined in the standard library or the standard prelude, you can of course define your own functions. And that's what writing Haskell programs is, just defining functions that do things. And the terminology is that new functions are defined within a script, and a script is just a text file comprising a sequence of definitions. So if you think about a Haskell script, it's just a text file, got a bunch of definitions, many of which will be function definitions. The last point here is that by convention, Haskell scripts usually end with a .hs suffix on their file name. So you might have something like test.hs. And this is not mandatory, but it's useful for identification purposes. So if you're writing a C program, you might call your file test.c or myprogram.c, and that's a nice reminder for you that it's a C program. If you're writing a Haskell script, you typically end it with a .hs. You don't need to do it, but it's useful if you're writing programs in different languages to always put the kind of file that you're writing as a suffix. And I will always do that in this course, and I suggest that you do too. So what we're going to do now is work through my first script. And this is something I definitely suggest that you do yourself. I mean, Haskell is it's a very sophisticated language, but we're going to be using it in quite a simple way in this course. But there's lots of different things that can go wrong when you start using Haskell. Maybe you haven't installed the system right, maybe your editor's not set up quite right. So please make sure that in the early days, in the first week of this course, you actually get the system installed or get access to it on our servers or in the labs and try out a simple example script like this to make sure that everything is working okay. So let me talk you through this, and this is something you should try for yourself. So when you're developing a Haskell script, it's useful to keep 2 windows open. One running an editor, I tend to use VI or Vim, as you may have seen already, and the other running the GHCI interpreter. So what you should do is start up whatever favorite editor you like, type in the following 2 function definitions, and then you're going to save it to a file. And I'll just say, let's call the file test.hs. So we're using the convention that Haskell scripts end with .hs. So there's 2 simple function definitions here. The first one is double of x is x plus x. Note we don't need any brackets around the parameter or input x because of the convention in Haskell. You don't put brackets around things unless you have to. And then the second example says if you want to quadruple a number, you can just double it twice. So you double it once in brackets, that will give you a result, and then you double that. Okay, and note in the quadruple case, you do need the brackets around the second double, because if you didn't put the brackets in here, what it would interpret it as is the first double function would be applied to 2 inputs, the double function and x, and that doesn't make any sense because double only takes a single input. So you need the brackets here to force this kind of cascading function application. You want to apply double once to the argument x, that gives you a result, and then you apply double to that result to get the final result that you want. So what you could then do is leave the editor open and in another window, start up the GHCI system with the new script. So I've got my little Apple command prompt here, and I type GHCI test.hs, and it will load the script in, and if everything's okay, then you can use functions from your script. And in fact, you can use functions from the standard library and your script as well. So for example, we might want to quadruple the number 10 and get back the result 40, or a bit of a contrived example, we could take double of 2 from the list from 1 up to 6, and double of 2 is 4, so we get the first 4 elements of this list. Nice and easy. But again, there's lots of different things that could go wrong when you're trying this for the first time, so please make sure in the first week of the course you try this stuff out and make sure everything works okay for you. So what you should do now is leave both of these windows open, go back to the editor, and then add 2 more function definitions, and then resave the file. And these are slightly more sophisticated ones, which illustrate some things about Haskell. So in the first line here, we're defining the factorial of n to be the product from 1 up to n. So for example, the factorial of 10 is simply the product from 1 up to 10. And this is a very nice, concise, one-line definition of what factorial does. If you're doing this in C or Java, you might use some kind of loop to do this. In Haskell, we tend just to use library functions wherever possible. So this is a very kind of high-level description, but still highly efficient because the compiler will make it so, of what factorial does. So we use the dot function to build a list between 1 and n, and then we simply apply the product to that. And one of the key messages that I want to convey in this course is that you shouldn't worry about efficiency. You write clear, simple, concise code and let the compiler worry about making it efficient, which it's very good at doing. So the second example here, we're defining a function called average, and what average does is it takes a list of numbers n's, and then it's going to compute the sum of the list and the length of the list, and then divide one by the other using the integer division operator div. And there's a bit of syntax here. I mean, div is just a normal function which takes 2 numbers, one after the other, and divides one by the other and gives you the integer divisor. But here, I've wanted to make it into an infix operator because it looks a bit nicer in my code here. And the way you can make any old function with 2 arguments into an infix operator is you just put back quotes around it. So there's an important point to note here. The quotes here are back quotes, not forward quotes. And forward quotes, as we'll see, are used for single character constants in Haskell, as they are in many programming languages. So it's a really easy mistake to make. I do it all the time as well. When I'm making functions into infix operators, it's back quotes, sometimes a bit hard to find on the keyboard, not forward quotes. And just down the bottom here, when you actually write x, f, y with back quotes around the f, that's really just syntactic sugar for f, x, y. So the compiler will actually take what you write there and transform it into the normal form before it actually starts to run your program. Okay, so a couple more examples. So GHCI doesn't automatically detect that script is being changed, so you need to reload it when you are finished editing your script and you're happy for the compiler to check it and run it for you. So you must do an explicit reload command. So you type :reload, it will read it in, check if there's any errors, and hopefully not, and then you could try running these 2 examples. So you could say, for example, what is the factorial of 10? And you get some big number, and you could say, what is the average of the list 1 to 5? And you get exactly what you expect, which is 3. So just before we move on, I want to show you some of the useful GHCI commands. There's zillions of these, but in this course, these are the only basic ones that we will actually need at all. So let me talk you through these quickly. So you can load a script in, you just type :load and then the name of a script from within GHCI, and that will just load it in and check it, and then you can play around with it. You can reload the current script. Sometimes it's very convenient to actually open up an editor from within the GHCI system, and in order to do that you need to tell the system what editor it should use. So you can say :set editor and then the name of your editor. So I have set things up, so I have :set vim, :set editor vim, and then I can use the vim editor automatically. You can edit a script once you set that thing up, and if you don't put the name of the script, it just said it's the current script. A very useful command, which we'll be seeing a lot of and we'll be talking about next time around, is :type. And what colon type does is you just give it any old bit of Haskell and it will check it and it will give you back the type of that expression. And that's very, very useful. We'll see lots of that in the course, and we'll see more about that next time. As I mentioned, there are many, many commands which GHCI has, and if you want to show them all and play around with these, just type colon question mark, and if you want to get out, you type colon quit, or just control D, or just kill the window. Okay, one thing to comment is you can also abbreviate all of these commands by their first letter. So if you want to edit a file, just type colon E. If you want to get the type of something, just type colon T, and so on. So when you see me using GHCI interactively with you, I'll typically just use the one character abbreviations for each of these commands. So the last thing I want to do is just a bit of admin stuff, but we have to talk about it because otherwise it will trip people up. The first thing I want to talk about is naming requirements. So Haskell is very flexible with names. It lets you choose all sorts of things as names for stuff. But there's one important rule that you need to remember, and the rule is function names and the names of their arguments must always begin with a lowercase letter. Apart from that, you can more or less do what you like. So here are valid function names or argument names, myFun with a capital F, fun1, arg_2 or x prime. These are all valid function or argument names. And the reason why they must begin with a lowercase letter is capital letters are reserved for things to do with types, as we'll see next day. For example, the integer type is spelled int with a capital I. So lowercase stuff is functions and argument names. Capital letter things beginning, or things that begin with capital letters, are things to do with types. And a simple convention, and you've actually seen me using this already, although I didn't mention it, I think, is list arguments usually have a .s suffix on their name. So they end with an S, and that's just a convention, helps you to kind of read things in a clearer way when you're looking at your programs, and other people's programs too. So if I had an argument of a function called x's, that's probably going to be a list. If I had an argument called n's, that's maybe going to, or likely to be, a list of numbers. And the last one here with two s's is interesting. If I see a parameter or an argument with two s's, and the first letter is n, that's probably going to be a list of numbers. Okay, so it's a very useful convention when you're writing functions, and I will be following this consistently, hopefully, throughout the course. The next thing I want to talk briefly about is the so-called layout rule. So Haskell tries to be very, very concise in terms of syntax, and one of the ways that it does this is it has this so-called layout rule, and it's very simple. When you make a sequence of definitions at the same level, each definition must begin in precisely the same column. So it's usually column 0 if you're editing at the top level of your code. So here's 3 examples to explain this. In the first example, which has got the big green tick, the definitions for A, B, and C are all lined up in the same column. The A, B, and C begin exactly at the edge of the blue box, so that's fine. The second one is wrong because I've put accidentally an extra space before the B, so that would be rejected as invalid. And the third one is wrong because I've put an extra space before the A and the C. So simple rule, when you have definitions at the same level in a sequence, they all must begin in precisely the same column. So what this lets you do is it lets you avoid the need for explicit syntax to indicate how definitions are grouped together. So when you write C programs or you write Java programs, for example, you need the curly braces or the squiggly braces and semicolons to indicate how things are grouped and separated. So you can still do that in Haskell if you want, but you don't need to do it because of this layout rule. And this is illustrated by this simple example here. In the left blue box, I've written 2 top-level definitions, A equals B plus C, and D equals A times 2. And then I've got 2 local definitions to A, one which says B is 1, and the other which says C is 2. And you can just see that these are local definitions because I've indented them. So your eye just parses these to say, well, okay, I've got a global definition for A, and B is going to be 1, and C is going to be 2 within that definition. So the grouping is implicit by the spacing which I've used. What this actually means is, Haskell still has the squiggly brackets and the semicolons behind the scenes. You can use them if you want. What it actually means is that, but I much prefer to actually write things without that. From time to time, if I want to fit bits of code on one line, rather than spewing them across multiple lines, sometimes I will use the curly braces and semicolons to separate things and indicate grouping, but primarily, and most Haskell code that you see will just use the layout rule, so you don't need to do that. It's very good at reducing the amount of stuff that you need to type. So to wrap things up today, what I want to do is think about a few simple exercises. Most of the lectures in this course are going to end up with a few exercises, and these are things that you should try out for yourself. So the first exercise here is to try out slides 2 to 7 and 13 to 16 using GHCI. So these were some simple things using the system. And again, what I've shown you today is all very simple. You might think, well, I'll just worry about this later. But there's lots of different things that could go wrong when you try and install the system, or you try and access it on the servers or in the labs, or there might be something wrong with your editor or something like that. So please make sure right at the start of the course, in some way or another, get access to GHCI and try out all of these examples and make sure that everything works okay. So the second exercise here is to do with syntax. So I've given you a 4-line Haskell program, and there are actually 3 syntax errors in this. So the exercise is to fix or identify and then fix these 3 syntax errors and then test your solution out using GHCI. So if you're watching this video in your own time, what you might like to do with these exercises is pause the video and try and solve it for yourself. And then for some of these exercises, I'll also be working through a solution with you as well. So for this example, there's 3 simple errors. These are quite easy to spot. The N at the start should be a lowercase n, because anything with a capital letter is to do with types. So here I'm just defining a constant n, and it's going to be the result of all of that stuff on the right hand side. So that should be a lowercase n. That's the first error. The second error is the quotes there around div are the wrong way around. And this, as I mentioned, this is a very, very easy mistake to make. Those should be back quotes, sometimes a bit hard to find on the keyboard. Those are forward quotes, which are used for single character constants, as we'll see later on. And the last error is what we've just been thinking about. It's the layout rule. The A here in the where A equals 10, that's got an extra space. The A and the X's are at the same level. They're local to that top level definition for n. So those have to be lined up in the same column. And I haven't done that, so the compiler would complain about that. So again, try this for yourself. Try typing it in and make sure that everything works out okay. Exercise 3 here. Show how the library function last that selects the last element of the list can be defined using the functions introduced in this lecture. So what I mean by this is at the start of the lecture I showed you about 10 or so simple functions on lists. The library function called last has a definition. It's actually defined using recursion, as you can look up in the library and we'll be thinking about later on. But you can also define it just by applying a few of these simple functions that we considered at the start of the lecture today. So see how, if you can figure out how the last function can be defined using some of these functions. And then exercise 4, can you think of another possible definition? And then the last one is, how can the library function init, which removes the last element from a list, be defined in 2 different ways. So again, if you're watching this video on your own, I'd suggest you pause the video at this point, try and solve these exercises on your own, and then what I'm going to do now is switch to my iPad and show you how to solve exercises 3, 4, and 5. But I suggest you have a go at this yourself first. So the first exercise we're going to be looking at is the last function. So let's have a little example first of all to see what the last function does. So if we started up GHCI and we get the greater than prompt, we could say if we take the last element of the list 1, 2, 3, 4, then what it's going to give us is exactly what we expect from the name. It's going to give us the last thing in the list, which is the 4. So we get that. So the name of the exercise here is to come up with a couple of different ways of selecting the last element from a list. So the first way is a kind of more traditional programming approach to doing something like this. We could just think about indexing into the list. So if we look at these list elements, this is the element at index 0. This is the element at index 1. index 2, and index 3. So what this tells us is if we want to access the last element of the list and pull out the 4 here, all we need to do is index in at the length of the list minus 1. Okay, so the length of this list is 4, but remember indexing starts from 0, so we'd subtract 1 and that would give us the right index. So this is a simple way how we could define the last function. So the last of x's is going to be, take the list x's, and then I'm going to index into it using the bang bang operator, which we saw today. And then I simply take the length of the list, which in the example case would be 4, and then I subtract 1 from it. Okay, so the length of the list is 4, subtract 1, you get 3, index in at the position 3 into the list, and you'll get the right answer. So this is a perfectly valid and simple way to define the last function using the library functions which we've seen today. But actually there's other ways to do it. So let me show you another way to do it. And this is maybe a way that you wouldn't initially think of if you're used to kind of more traditional imperative style programming. So what we could do here is if we look at the input list which we have, so we have 1, 2, 3, 4, if we think about reversing that, so if we reverse that list, that would give us 4, 3, 2, and 1. And then what we could do is if we want to select the last element of the original list, if we take the head of that list, which is the 4, so sitting here, that will give us back exactly what we want. So we could simply cascade these two functions together to give us a definition of last. So let's define that. So we could say, as an alternative way to define last, we could say last of x's is simply head of reverse of x's. So in the example above, we reverse 1, 2, 3, 4 to get 4, 3, 2, 1. We take the head of that, and that will give us back the 4. So this is a very different way of thinking about things than you might think about in a more traditional programming language, because in those languages you tend to worry about efficiency an awful lot. And if you think about a program like this, you might think, well, reversing the list might take quite a bit of time, and I don't want my programs to be slow, so I'll do it just by indexing in at the appropriate place. And one of the key messages I want to get across to you in this course is when you're writing Haskell programs, they're very high-level programs, you should focus on writing clear, concise, and correct code, CCC, I'll be saying this many times in the course, clear, concise, and correct, and let the compiler make it efficient for you, which it is very good at doing. Okay, so a key message, write clear, concise, correct code, don't worry about efficiency, and because that's the compiler's job. Okay, so for me, this is more of a kind of Haskell style definition. The other one's perfectly fine, and if I asked you in an exam to define last, any definition which worked would be fine. But this is a kind of more Haskell-y one, if you like. Okay, so let's have a look at the final exercise now, which is to do the same thing with the init function. So what the init function does is you give it a list like 1, 2, 3, 4, and it does the opposite of last. It gives you everything apart from the last element, so it's going to give you back the 1, 2, 3. And the reason it's got a silly name in it, it stands for initial segment. So 1, 2, 3, some people call the initial segment of this list. I don't like that name. It's a kind of silly name. So how could I define this function? Well, there's two simple definitions for this. So let me give you one first of all. One thing which I could do is I could say, if I want to take the initial segment of this list, all I need to do is take the length of the list minus 1, because this list has 4 elements in it, and I only want the first 3, I want everything apart from the last one. So if I simply take the length of the list, length of x's, minus 1, if I take that from the list, that is a valid definition for init. Okay, so I'm computing the length minus 1, which in the example would be 3, and then I take 3 elements from the list, and that will give me back the first 3 elements. So that's a nice, simple example. So let me show you another kind of more Haskell-y way of doing the same kind of thing. Let me define it alternatively. I could say the initial segment of a list. What I could do is cascade 3 functions together. Okay, and again, if you're used to more traditional languages, you might not think about doing something like this because you worry about efficiency. So what is this doing? Well, what we're doing, in order to take the initial segment of list x's, so that's everything apart from the last element, what I'm going to do is first of all reverse the list. So if I took my example, I'd reverse 1, 2, 3, 4, and I get 4, 3, 2, 1. Then I take the tail of that, so that would give me the 3, 2, and 1. It would remove the 4, and then I reverse that, and then I get back to the 1, 2, and 3. So again, a more Haskell-y style way of defining this function. But any old way you could define this would be perfectly valid. So that's it for today. I will see you again next